Assalamu alaikum students. In today's lesson you will learn about sp2 hybridization along with the structures of BF3 and ethene, as well as you will also learn about sp hybridization along with the structure of beryllium chloride and structure of ethyne. Before I start sp2 hybridization, I think you know very well what is meant by hybridization. Hybridization is the mixing of orbitals of different shapes and different energy to give new energy forms of orbitals and the same shape with the same number of the orbitals. Here in sp2 hybridization, as the name is indicating, one s and two p orbitals, they fuse or they mix together to form three new orbitals of the same shape and same energy. As the shape of s orbital is spherical while of p orbital is dumbbell shape. Now the three new orbitals formed will be termed as sp2 hybrid orbitals. No more they will be termed as s or p orbitals. The energy of these hybrid orbitals is always lower than that of the unhybridized orbitals. The percentage of each one, that is s and p orbital, in this type of hybridization is, as you can see, there is only one s orbital and two p orbitals which overlapped in. So out of 100, the 33.33% of the s orbital is being present, while the 66.66% character is of the p orbitals. So domination is of p orbitals. Now the sp2 orbitals, they arrange themselves in space in such a way that the distance between them is maximum and the repulsion between them is minimum. So they get a shape of trigonal planar with an angle of 120 degrees. Right, now here consider some of the simple examples that how this hybridization takes place. Before it, a general, now this is the pictorial evidence of sp2 hybridization. You can see here three orbitals of different energy and different shape, they have been mixed together. Number one, it is s orbital, which is spherical in shape. Number two and the number three, both of these are dumbbell shapes of the p orbitals. Now the three mix together to give the three new orbitals with the same energy and same shape, as it's being told earlier that they are of the similar energy, and the energy of these hybrid orbitals a little bit lower than that of the unhybridized orbitals. These three hybrid orbitals, these ones, they assemble in such a fashion that they produce a trigonal planar geometry around the central atom. Here it is given the central atom around which these three orbitals, they assemble themselves with an angle of 120 degrees between them, and the shape is there, that is trigonal planar geometry. Now, as I told you earlier, that this happens only with the central atom orbitals, right? After the central atom has prepared it for the bonding, after hybridization, it will attract the orbitals or the electrons of the other one atom to produce bonds. Now here the structure of boron trifluoride has been discussed. Boron trifluoride have a formula BF3. This is the way that how you have to give it in exams. Now here, first of all, you have to write the electronic configuration of boron and fluorine separately. Here you can see boron with atomic number 5. It has the ground state electronic configuration, that is 1s2, 2s2, 2px1, 2py0, while 2pz is also 0. Now here there comes an excited state. It is presented by B star. This excited state shows that one of the transition of electron from 2s to 2p takes place, by which 3 unpaired electrons originate, means it can go for 3 bond formations, right? After this excitation, now it will go for hybridization. The mixing of these 3 orbitals takes place, namely 2s and 2px, 2py orbitals. They will join together to form 3 sp2 hybrid orbitals, leaving behind one of the p orbital that will be of its original shape, that is the dumbbell shape, right? Now here the structure of boron trifluoride has been given. You can see in the center there is present boron with 3 of its hybrid orbitals. Each one is sp2 hybrid orbital. This one, number 1, number 2 and number 3. Now each one is sp2 hybrid orbitals. They are assembled in trigonal planar form. Now each fluorine have atomic number 9 with this configuration: 1s2, 2s2, 2px2, 2py2 and 2pz1. There is only one electron available in pz orbital, and you know very well what is the shape of the p orbital. It is dumbbell shape. So we have to show overlap of the one of the p orbital of each fluorine atom with that sp2 hybrid orbital of boron in this way. Here it is first overlap, this one is the second overlap, and this is the third overlap. You can see here the two orbitals, they overlap to give sigma bond formation. So there are 3 sigma bonds formed between 2 orbitals by the overlap of the sp2 orbital of boron and p orbital of fluorine. 3 fluorine each is going to make one bond with the central atom. So we say 3 sigma bonds are present between BF3. Here you can see it is given another arrangement. This one is BF3 where the central is the boron, and while the 3 blue colored balls, they represent the boron with a trigonal planar geometry with an angle of 120. And if we want to show the dot cross model, so here it is given, that is in the form of a Lewis structure. Here you can see boron is linked with 3 of the fluorine atom. On fluorine atom there are present 3 lone pairs with each fluorine atom which are not participating in the bond formation, but the only bond is formed by the unpaired electron which was present in the pz orbital of the fluorine atom, right? Similar structure will be given if we make for the BCl3, or what to say, it is the sp2 hybridization which is given by BF3. Another thing, boron in excited state shows 3 unpaired electrons which is helped by means of the hybridization. Otherwise it should have valency of only 1, right? But it shows valency 3. This 3 valency is explained on the basis of its excited state which is given before hybridization, right? Now here the structure of ethene is explained. Ethene having formula CH2 double bond CH2 C2H4 is the molecular formula of ethene. In it, carbon shows valency 4, that it has 4 unpaired electrons in its outermost shell, so it exhibits the sp2 hybridization. How it shows sp2 hybridization, that is explained now. Look at the ground state of carbon atom. It has valency according to this ground state configuration. It shows valency 2, that it has only 2 unpaired electrons in it. But when it undergoes excited state, one of electron from the valence shell 2s moves to the 2pz empty orbital here, so that what happens, the valency of carbon becomes 4. So this is hybridization, which explains how carbon shows tetravalency in most of its compounds, right? Now here the carbon undergoes sp2 hybridization. I hope you are familiar now. sp2 hybridization means one s and two p orbitals are mixed together to produce three identical in shape sp2 hybrid orbitals. None of them will be called now as s orbital or p orbital, but they all will be termed as a new type of orbitals, that is sp2 hybrid orbitals. So here you can see the 1s2 orbital is retained as such, while the other three are occupied by one electron, while one electron, unpaired electron, is also present in the unhybridized p orbital. Right? Now here the structure of ethene is given under this hybridized structure. Here you can see in this structure, each carbon of C2H4 is sp3 hybridized separately. Each is having three hybrid orbitals termed as sp2 hybrid orbitals. They are assembled in a trigonal planar geometry. Now each orbital will overlap with the, here it is given, each hybrid orbital of the carbon atom overlaps with the hydrogen atom of spherical shape to give an sp2 to s overlap. This is a linear one formation of the electronic cloud. So the bond formed is a sigma bond. Here for the second one, same as here, sp2 to s overlap. Similar on the other side with the other carbon, there are two sp2 to s overlap. While in the center, the two carbon atoms, they join together by means of sp2 to sp2 overlap. All these shows sigma bonds. Now in total, we have assembled only hybridized orbitals, right? Still each carbon have its p orbital with the half-filled electrons in it, right? Now here we have in total 5 sigma bonds formed by the ethene molecule. 5 sigma bonds. This is also a type of the short question asked in the MCQs, right? There are present 5 sigma bonds in this ethene molecule. Now this is the shape which appears as this one when p orbitals, which are retained further, they overlap with each other in a sideways overlap. This one, they gives a sideways overlap. This sideways overlap produces the region above and below. Remember it, these two orbitals are with their own identity. There is no mixing of orbitals took place here for these two p orbitals, right? So they will form a pi bond formation where the electronic cloud is present above and below the plane. Here a three-dimensional arrangement is mentioned in this structure. You can see two of the carbons three-dimensionally, they are attached in a trigonal planar geometry. Remember it that each carbon separately exhibit trigonal planar geometry, right? So overall, in an ethene molecule, there are 5 sigma bonds and 1 pi bond present, right? Now come to the next one. Here it is given sp hybridization. As the name indicates itself, that one s and one p orbitals, they overlap or they mix or they intermingle or they fuse to produce two new orbitals of same energy and same shape. You can see every time hybrid orbitals, they have the similar shape and energy because they have the mixing of s and p orbitals. So the shape is same in all the cases. Here we can say there is present s and p, 50% share of both is there. So there is a domination of s character, that is 50% means before there was the domination of p characters. Now this time it is the equal one. between S and P, so it is the strong one bond, right? It gives the strength. Now here we have the assembling of these two p orbitals will comes out in the form of a linear fashion with an angle of 180 degrees, right? So a linear geometry appears. Now come to some of the examples that how does it happen. Mixing of orbitals. Now here you can see the two orbitals, one s and one p orbital, with their individual or the pure one shapes, they mix together. Before they were high in energy, after mixing they are now in low energy state. Now they have two of them are being mixed, so two new orbitals are formed of the similar energy. Here these two orbitals are like this. You can see the shapes are same as we have done before. Assemble them in such a way, it is just like you took pick up the balloons from the center, right? So pick up two of the balloons from the center. They will come and then just hold them in the space. What will happen? They will assemble themselves in a particular geometry or a shape. The geometry which they will give rise, that is a linear geometry. Here you can see, right? Now this linear geometry is having the angle of 120 degree where these two orbitals are apart from each other. Right, Ji? Now the structure of beryllium chloride has been discussed here. In beryllium chloride, the central atom is Be. Here it is BeCl2, which will be formed by it. This central atom is having valency of 2. How? This is explained by means of this hybridization approach. You can see in ground state beryllium with atomic number 4, it has the electronic configuration 1s2 and 2s2. According to this configuration, it shall not form any bond as it is quite satisfied with the paired of electrons in its 2s orbital. But it undergoes hybridization. Before this hybridization, it undergoes an excited state in which the 2s electron transits one of its electron, the 2s orbital transit one of its electron to the 2px orbital. So it now have two unpaired electrons in 2s and 2p orbitals in each. So now it can go for two bond formation. Before it go for bonding, it undergoes hybridization. So two of the orbitals they mix together to produce two hybrid orbitals. They will be termed as we have mixed only one s and one p orbital. So it will be now termed as sp hybridization, and there will be formed two sp hybrid orbitals, right, which will assemble themselves in such. Now here the structure of beryllium chloride is given on the base of hybridization. As you can see in the central atom beryllium, the two orbitals, they are the hybrid orbitals, they arrange themselves in a linear fashion, in a linear geometry with an angle of 180 degrees. Now here the chlorine atom with atomic number 17, its outermost configuration is 3s2 after neon. It is, that is the shorthand configuration. Outer shell configuration is 3s2, 3px with 2, 3py with 2, and 3pz also with 1. Now here it is capable to form only one bond as it is given. It has one unpaired electron in 3pz orbit, right? All the other pairs in the outermost shell, they will comes out as the lone pair of electrons in chlorine, right? So there will be present three lone pairs in chlorine atom each, and it will hold just one electron which will go for bonding. Here it is given, the p orbital of chlorine with the dumbbell shape overlaps with the sp hybrid orbital of beryllium to form a sigma bond. On the other side, the same is done. The p orbital of chlorine overlaps with the central carbons, central beryllium sp hybrid orbital to produce a sigma bond. So in total, in beryllium, there are present two two sigma bonds, right, to give two covalent bonds between the beryllium and fluorine atoms. This is how the structure of beryllium chloride is explained on the basis of hybridization. Now to the next one, it is the last structure of ethyne, which is explained on the basis of sp hybridization. You can see carbon is a unique molecule which undergoes all the three types of hybridization, that is sp3, sp2 and sp as well, so that it shows single bonding in sp3, it shows double bonding in sp2, and it shows triple bonding between the two carbon atoms in sp hybridization, right? So it can form multiple bonds under different conditions of hybridization. Again, you have to explain its ground state, then you have to give its excited state. In its excited state, you can see now, I think there is nothing to explain now for carbon. Here it is given that in excited state, it has 4 unpaired electrons, showing that it has valency 4. These 4 electrons are responsible for 4 bond formation by carbon atoms. Now, among them, only 2 orbitals will get mixed, that is one s and one p orbital, to form 2 sp hybrid orbitals, while the other 2 p orbitals with their identity are retained as such, which will undergo to form the pi bond formation. Right? Now here the structure of ethyne is explained on the basis of sp hybridization. The ethyne molecule can be given like this. It is arranged in this way that carbon to hydrogen 1 bond, carbon to carbon there is present a triple bond, and there another carbon to hydrogen bond is present, as it is given below. You can see here each carbon is separately sp hybridized. 2 hybrid orbitals of this carbon and 2 hybrid orbitals of this carbon. Each orbital will be termed as sp hybrid orbital. Now they are arranged in the linear fashion with an angle of 180 degrees. Now two carbons, they have overlap of their sp hybrid orbitals in the center. Here it is given. Look at this. This is sp to sp overlap called, and it is also a sigma bond which is formed. The second overlap is between one of the hybrids of one carbon and the hydrogen atom with their symmetrical s orbital, while on the other side also there is an overlap between the s orbital and that of the hybrid orbital of the carbon atom, that is sp. So it is sp to s overlap. It is also a sigma bond formation. So in total in ethyne there are present 3 sigma bonds, but it still has 2 of its p orbitals, each with 1 electron in its orbits. What happens here? They will overlap to give, here it is first overlap between the 2 orbits, second overlap between the 2 orbits to give 2 pi bonds. In the earlier lecture we have discussed that among 3 p orbitals, when they all are getting bonded with the other atoms, so one of them will make sigma bond while the other 2 will make pi bonds. Right? Now here it is given 2 pi bonds will be formed. So in between carbon atoms there will be present a high charge density or electronic cloud, that you can see here 3 pair of electrons are present over there. If I present it by means of the other structure, that I show the bonds here or the electrons here like this, 1 pair of electron, second pair of electron, and 3 pair of electrons are being present between the 2 carbon atoms, and between carbon to hydrogen there are present 2. one of the pair of electron between these two. Here it is given, you can see this one like this, right? Now here we have the maximum charge density present between the two carbon atoms. So this area is rich in electron cloud. Here how the structure of ethyne is explained on the base of hybridization. Once again, if you are asked that how many bonds are present in ethyne, so you have to say that 3 sigma bonds and 2 pi bonds in total are present in ethyne, right? Now this one is all about hybridization.